Let us look at proposition number 20 of book 6 of Euclid's Elements. The proposition says similar polygons are divided into similar triangles and into triangles equal in multitude and in the same ratio as the wholes. And the polygon has to the polygon a ratio duplicate of that which the corresponding has to the corresponding side. So basically, the proposition says that we can divide this into similar triangles. So here we could say ABE is to FGL equal to CBE is to HGL and CED is to HLK. All these ratios would be equal and the polygons would also be in the same ratio. And the ratio of the polygons would be equal to AB square is to FG square. That is the ratio duplicate of the corresponding sides. Okay, let's see how we can take it step by step. Let's join BE and let's join GL. Since these are similar polygons, we know angle A would be equal to angle F. Yes. And since these are similar polygons, we also know that BA is to AE equal to GF is to FL. But restricting ourselves to these triangles, this and the fact that A is equal to F, we can say triangle BAE is equal to GFL. Since they are similar, that means angle ABE is equal to angle FGL and angle AEB is equal to FLG. Since angle ABC is equal to FGH because the polygons are similar. So since these angles are equal and a part of those angles are equal, that means the remaining angles will also be equal. Because of the similarity of triangle ABE and FGL, we can say BE is to AB as GL is to FG. Angle EBC equal to LGH. Just now we saw why. And we know because they are similar polygons, AB is to BC as FG is to GH. That means AB is to B. Yes. That means we can combine these two proportionalities and say BE is to AB is to BC is equal to GL is to GF is to GH. Which means we can say B is to BC, BE is to BC as GL is to GH. So we have these sides in proportion and the sides are about the equal angles. So which means if we join EC and HL, then triangle EBC is going to be similar to LGH. Similarly, we can prove triangle ECD is similar to LHK. Now let's join AC and FH. Triangle ABC is similar to triangle FGH. We can prove that easily because we know angle B is equal to angle G. We know since these two are similar polygons, these angles are equal. But we also know AB is to BC equal to FG is to GH. So these two triangles are similar. Similarly, we can show triangle ABM. M is nothing but this intersection and N is this intersection. ABM is similar to FGN because ABE is similar to GFL. That means angle ABC is nothing but ABM. So this angle is equal to FGN. We would have proved ABC is similar to FGH. So that means BAC is equal to GFH. That means two angles are equal to two angles. That means the third angle is also equal. That means it is equiangular, which means we can say ABM is similar to triangle FGM. Similarly, we can show that triangle BMC is similar to GNH. See here, this angle is equal to this angle. We can similarly figure out to show that the sides are in proportion. That means BMC is similar to GNH. Since it is similar, we can say AM is to MB as FN is to NG. Also say MB is to MC as NG is to NH. Combining these two proportions, we can say AM is to MB is to MC is equal to FN is to NG is to NH. Which means we can say AM is to MC equal to FN is to NH. Now let's look at AM is to MC. AM and MC, on those are in a straight line, and on that these two triangles are there, ABM and MBC. That means they are under the same height. So that means those triangles would be in the same ratio as their bases. Similarly, these two triangles are also under the same height. So they will also be in the same ratio as their bases. So we can say AM is to MC is equal to triangle ABM is to triangle BMC is equal to triangle AME is to triangle EMC. Here, this ratio, we can say it is equal to the ratio of the sums. So ABM plus AME, ABM plus AME is nothing but ABE. And similarly, BMC plus EMC is nothing but CBE. So we can say triangle ABM is to triangle BMC is equal to triangle ABE is to triangle CBE. So AM is to MC we have seen. Now let's look at FN is to NH, right side of this. Since FN is to NH, FN is to NH. Here also following the same logic, we can say triangle ABE is to triangle CBE. Triangle ABE is to FGL is equal to CBE is to GLH. How did this equality come? Because remember here we have already shown AM is to MC equal to FN is to NH. AM is to MC is triangle ABE is to CBE. FN is to NH is triangle FGL is to GLH. Okay. Now let's take the alternate ratio. So triangle AB is to triangle FGL is equal to triangle CBE is to GLH. Similarly, we can show that triangle CBE is to GLH is equal to triangle ECD is to LHK. So we have shown that we can divide this polygon into similar triangles, and these similar triangles will be in the same ratio, which is what basically similarity means. But the important thing is the overall polygon would also be in the same ratio as the ratio of these triangles. Since we have seen in a proposition that the ratio of 1 will be equal to the ratio of the sum. So which means triangle ABE is to FGL will be equal to the sum of the individual ratios of the triangles. So ABE plus BC plus CED would be equal to what? ABC DE. And here the sum would be FGHKL. That is the whole polygon. So which means triangle AB is to triangle FGL is equal to polygon ABCDE is to polygon FGHKL. But remember, we had one more proposition which said that a triangle is to a triangle similar. In case of similar triangles, the triangles would be in the same ratio as the duplicate ratio of the sides, corresponding sides. So we substitute this into the left hand side. So we get polygon ABCD is to polygon FGHKL is equal to AB square is to FG square. So that is proposition 20 of book 6 of Euclid's Elements. Take it step by step and try to understand. If you would prefer reading through it, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it and refer to it. And in case you think somebody else can also benefit from it, please do share it. That's it for now.